Hello and welcome to today's session. We are going to continue with our frequency response for the differential operation, and we are going to look into the stability analysis, the application of Miller compensation as we did for the common mode case. So, let us look at the frequency response of the fully differential operation, for which I am drawing the entire two-stage amplifier again. And here we have the input and the output. So, we have already identified the critical poles in this circuit. We mentioned that the load terminals of the first stage are going to produce or going to offer relatively high impedance. Therefore, you have RO over here, RO by 2 impedance coming over here. As a result, this is a high impedance node. This is going to give us the first critical pole, and likewise in the output node, once again the overall impedance is RO by 2. This is the second critical node for which we need to figure out the poles. So, for the AC half circuit, we are going to deal with only the differential half circuit, where you have AC ground at the common source point of the differential pair. Therefore, we are left with our common source amplifier with PMOS active load NMOS input device, and second stage is anyway a common source stage, where you have a PMOS as the input device and NMOS as the load device. And here we know that the overall differential gain that we are looking at is GM RO by 2 whole square. So, this is the information we discussed last time, and once again looking at the two stage topology, we have to arrive at a proper compensation scheme. Just like we did for the common mode case, here also we can take the help of a compensation capacitor, so that one of the nodes is pushed towards very low frequency and we get good phase margin. And to do that, we can exploit the gain of the second stage and put a compensation capacitor between the output of the first stage and output of the second stage. So, let us put compensation capacitors between the output of the first stage and the second stage, and we know that the result of this will produce an equivalent capacitance C1 dash, I can call it, or CC1, which is the equivalent component resulting from the CC at the first node, and that is going to be A2 times CC approximately, where A2 is the gain of the second stage. And at the output, we are going to get CC, I can call it CC2, which is the equivalent capacitance resulting at the second node or the final output because of CC2, and which is approximately going to be CC only, because this is going to be CC times 1 minus 1 upon A, where A is large, and therefore, it is approximately CC. So, this is the condition we have, and apart from that, we can have an additional load capacitance, which is because of the subsequent stage, the next stage coming. So, you can have an additional load capacitance CL also. So, for example, if this particular stage is driving another amplifier which is having another capacitive feedback, and it is having a large input capacitance of few picofarads to just give you a larger gain, that can act like the load capacitance of this stage. So, that is coming from the next stage. So, and in general, that CL can be sufficiently larger than the other parasitic components at this node. So, that will be given by the input capacitance, effective input capacitance provided by the next stage. Likewise, since we have a fully differential operation, you have the same thing on this side as well. So, I am focusing on one side. So, same thing because of symmetric operation, you will get on the other side as well. Now, here what are the relations we need to follow for obtaining the overall 45-degree phase margin? Just like in the case of our common mode operation, we are going to have similar analysis here, and our target would be to make the second pole or the non-dominant pole A naught times the dominant pole. So, the lower frequency pole, as we said, that is going to be pushed towards low frequency, and we want the second pole, that is the non-dominant pole, let us call it P2. We want P2 to be A naught times P1, where A naught is the low frequency gain of the two stage, that is A1 times A2. And For that, first of all, we need to look at what is the P1 and what is A naught. So, for A naught I can write it down as GM1. GM1 means the gain, the GM of the first stage times R R1, that is the total output resistance of the first stage, that is just ROP parallel RON. So, if I say the total output resistance at this node, that is ROP parallel RON for the differential operation. Remember, for the differential operation this is at AC ground. So, in order to find out P1, I need to find out the R equivalent and C equivalent at this particular node, and the R equivalent is basically RO of the PMOS coming between this node and AC ground, and likewise RO of NMOS coming between the output node and another AC ground. So, therefore, it will be RON parallel ROP, and that is what I am mentioning as R1, that is the small signal output resistance of the first stage effectively, and GM1 is the GM transconductance of the first stage. So, GM1 corresponds to the transconductance of the input pair. So, here the subscript denotes the stage, the first stage GM1 R1, and then you have the second stage, the low frequency gain. Second stage, once again I can write them down as GM2 R2, where GM2 will correspond to the GM of this transistor, and R2 will be the overall small signal resistance at this stage, which is basically ROP parallel RON once again at this particular stage. So, this is the A naught, that is the overall low frequency gain from the input to the output. I remember, while calculating the low frequency gain, we do not consider the other parasitic components, parasitic capacitances and their frequency effects. And then we also need to find out the P1. So, for the P1, we know that the overall capacitance at this node has been modified as A2 times Cc, which is basically nothing else but GM2 times R2, and then you have the overall small signal resistance still given by the R1. So, this is your P1. So, here we can get R1 cancelled, and you have A2, which is basically nothing else but GM2 times R2. So, this is your A2, and therefore, these two factors also get cancelled, and therefore, you are left with GM1 upon Cc. So, what I want to do is I want to make the P2 equal to GM1 upon Cc. So, this is the relation that I want to have. Now, we also need to look at the second pole. What is the expression for the second pole that we are going to get? So, for that we need to look at the resulting small signal resistance and capacitance at this node. Now, if I assume that this CL, which is coming because of the next stage, maybe in this case the next stage amplifier or filter. So, assuming that CL is sufficiently greater than all other parasitic capacitance at this stage, we can assume that the total parasitic capacitance C equivalent at the second stage is dominantly CL. So, assuming that to be true, I can write down the C equivalent as CL at this point. Now, the other question is, what is the R equivalent at this point, that is what is the small signal resistance at this point. So, if I look at low frequencies, definitely for writing the gain we have used the overall R equivalent at this point equal to the RO of P parallel RO of N, that is giving us RO by 2. But if you are looking at frequencies much beyond P1, there are certain effects coming because of the Cc, the impedance of the Cc going low, which is going to degrade the overall small signal impedance at this node, and let us see how does it give us an advantage in terms of compensation of the overall amplifier response. So, in order to look at the overall impedance at this node, overall small signal impedance at this node at frequencies much higher than the first pole P1, we can draw the equivalent circuit. I am going to draw a equivalent circuit for this particular second stage, where I can model the second stage, the first stage over here by its equivalent output impedance. I can call it RO1 or R1, and at this node I have some equivalent capacitance coming over here between this particular node and the AC ground because of all other components. So, I am retaining the Cc, and I am saying that in the actual amplifier, if I look at the actual first stage, this is the first stage giving me A1, you have certain output resistance. So, I can model its equivalent output resistance as say R1, and along with that you have some capacitance C1, which is because of the parasitic capacitances of the MOSFETs, the NMOS and the PMOS. And then you have the Cc, which is connected from the output of the first stage to the output of the second stage. So, here I have the Cc connecting the output of the second stage from that of the first stage. And likewise, at this particular point I also have the total R, the small signal resistance of the second stage. I can call this say R2. So, at this particular point I am modeling these two MOSFETs, the effect of these two MOSFETs as R2. So, that is the small signal resistance of the NMOS and PMOS combined, R2. And now my purpose is to just find out what is the overall small signal resistance looking into the output node at frequencies much higher than P1. So, for that I would like to inject some test voltage over here Vt and try to observe the It, what is the small signal current. That is how we find out the overall impedance, small signal impedance looking into a particular node. Effectively what I am doing is I am just putting a small signal voltage over here at this node and trying to find out the resulting It, and for that I am modeling this overall two stages as the equivalent resistance and capacitances at those stage. For example, here I have the second stage, I am modeling it as the R2, which is the R up parallel R down of this stage. Cc is connecting the output of the second stage from the output of the first stage, and the first stage is once again modeled by the equivalent parasitic capacitance C1 at this stage and the R1, the total small signal resistance coming at this stage because of the amplifier. So, here I have not applied any Miller effect, I have not broken Cc, I am just looking at the exact behavior, how is it going to behave at very high frequencies. The point to be noted here is that the Cc is much larger than the parasitic capacitances provided by the first stage. So, Cc is much larger than C1, and we are assuming that we are at sufficiently high frequencies. So, we have crossed the first pole P1 and we are sufficiently higher than that. As a result, the 1 upon omega C1, the impedance of this component is dropping as compared to R1. So, if I make that assumption, then I would assume that the parallel combination over here is dominated by the impedance of this parasitic capacitance 1 upon omega C1. So, that is the assumption I am making because I am at relatively high frequency. So, in that case what I can say is the overall voltage coming over here, I can call it the Vg of, if I call this 6 M6, because this is when number is 1, 2, 3, 4, 5 and 6. So, let us call it M6. So, the total voltage over here Vg6, this is a small signal voltage coming over here because of the applied signal Vt over here. And if I assume that the overall impedance in this parallel branch is dominated by the C1, which is the parasitic capacitance at this node, my Vg6 over here will be given by the ratio of these two capacitances, the voltage division provided by these two capacitances. And because my Cc is much larger than C1 because of the capacitive voltage division, we have the impedance of this one much smaller than the impedance of this. As a result, Vg6 is going to closely follow Vt, and therefore, this node is going to very closely follow Vt. So, what we are trying to say is that at lower frequencies the Vg6 starts following the output signal over here very closely, and as a result what we are effectively having is there is the two nodes are effectively getting short circuit from the point of view of AC. So, effective impedance seen between these two nodes is degrading, and effectively if these two nodes get shorted, the M6 over here behaves or starts behaving like a diode connected MOSFET, whose impedance looking into the drain will be approximately 1 upon GM6, or in other words following our earlier nomenclature GM2, that is the GM of the second stage. So, the conclusion out of this is that we are having a reduced effective impedance at the second stage because of this bypassing effect provided by CC at high frequency, which basically is going to push the second pole at much higher frequency, rather than having an overall impedance over here given by RO by 2, we are having an effective impedance at high frequency given by just 1 upon GM6, which is the small signal impedance provided by M6 when it is getting effectively short circuited, when the gate on the drain of the MOSFET M6 is getting effectively short circuited. So, the P2 expression, if I have to write down, that will be given by 1 upon the effective small signal capacitance here, and assuming that that is dominated by CL, I have the overall impedance over here given by 1 upon GM6. So, it basically goes up and I have GM6 or basically GM2, that is the transconductance of the second stage as we have defined. So, in order to achieve 45-degree phase margin, we want to make this equal to the gain bandwidth product that we have just arrived at, which is our GM1 upon CC. So, this is the relation we would like to obtain in order to have a 45-degree phase margin in this circuit. So, as we have said, if you are going for single loop, the same capacitor can compensate the common mode as well as the differential operation. So, for the common mode also same capacitors will be coming into picture when you consider the loop, if you are having a single common mode feedback loop. So, that also has been discussed in the class. If you have separate loops, then of course, the two loops have to be compensated separately. If it is a single loop, then we will see that even the error amplifier, the common mode feedback is not going to have significant, the pole of that amplifier is also going to lie at very high frequencies. So, as we have discussed, that if you are having a single loop, in that case, just to reduce the overall loop gain, we keep the gain of the error amplifier pretty small by having a direct connected load for both the drains, and in that case the dominant poles are coming only from the first two stages of the amplifier, and the error amplifier does not contribute significantly to the pole. So, in that case we need to compensate the P1 only, that is the main dominant pole for the differential response as well as the common mode response. So, we will revisit that once we finish this. We will complete the common mode feedback circuit also, and try to make sure that both the loops are getting satisfied, both the loops are getting compensated. Any other question?
What was happening when we were putting a buffer amplifier before putting CC?
So, there was just to isolate the common mode from the differential. So, here also we will see that ultimately to tackle some other issues we may need to put a buffer. So,
then the R of the second stage will not be 1 by GM.
That is when you are using separate loops. So, if you are using separate loops for the first stage and second stage for the common mode feedback, then that is the result. But if you are using single loop, then you have the same capacitance compensating both of them. Okay, so we can go towards the other issue which comes up with this CC, and that is the case of zeros. So, we have ignored all throughout the zeros coming up in the differential amplifier or the operational amplifier circuits, and that they can also play very crucial role in determining the overall stability. They can affect your stability in a negative manner. So, let us look at the concept of zero. How does it arrive in this circuit, and then what is its effect on the overall phase response, and then how to resolve that effect using some appropriate components to be added in the feedback loop. So, here if I look at the second stage, you are having the CC between the input of the second stage and the output for compensation, and as a result we have two different signal paths, one coming from the input to the output through the CC, and another one coming from the drain of the MOSFET. So, if I, for example, if I isolate these two, if I isolate these two and assume these are two independent signals being applied at the input of the second stage. So, suppose although they are same signals, but I am just disconnecting them and assuming that they are two different signals. So, from the input of the PMOS we have one path, we can find this overall output voltage as a superposition of these two signals. So, one coming from the input of the MOSFET to the output, and you have an inverting gain. If I get the effect of V applied at the gate of the MOSFET to the output, you have an inverting gain. Whereas, if I take the effect of this particular V on the output, you have some overall voltage division provided by this capacitor and the overall impedance over here, which can be relatively in phase of the applied signal over here. So, if at some frequencies the signals provided by these two paths at this particular point have exact cancellation because of having a 180-degree phase shift over here and relatively positive phase over here, these two signals can combine in a destructive fashion, and at a particular frequency, if they cancel out each other, then you have a zero, because the overall signals, the overall small signal coming over here from these two signal paths, the inverting one and the non-inverting one will be 0, and that is going to give us the frequencies of the 0 in this circuit. So far we have ignored the zeros, and that happens because we are taking approximate analysis. We are assuming Miller effect and breaking down the capacitance at different nodes. So, we are ignoring the signal propagation through these capacitances at higher frequencies, and remember that the concept of Miller effect that we use has inherent approximation, that the same gain, the low frequency gain, is valid at higher frequencies at which we are applying those capacitances also, which is also not true, because when we apply Miller effect and take the low frequency gain, that is valid for the pass band or low frequencies below the dominant pole of the circuit. As we go towards higher and higher frequency, the gain also reduces, which we do not take into consideration while applying our approximate analysis using Miller effect. So, if we look at this particular combination, I can write down the expression for the output signal over here as a superposition of these two. So, I can write down V out as V times the capacitive division between the voltage division between this capacitor and the overall impedance over here. So, I am going to represent the impedance of this MOSFET, say, as R. So, suppose the small signal resistance provided by this MOSFET NMOS is R, which we know is RO by 2. So, here if I look at the you can assume that the total impedance, total small signal resistance provided at this node by the combination of this PMOS and NMOS is R. So, you have ROP looking upward and RON looking downward. So, the small signal resistance R, I am assuming, is combination of RON parallel ROP. So, effectively, if I am looking at the voltage division, this particular voltage is applied to a voltage divider formed of this capacitor Cc and R, or rather R. So, this is V out, the expression of V out because of this particular signal is just going to be V into R upon R plus 1 upon SCC. And for that, while considering this, we have to consider that the other V is set to 0 because we are taking superposition. So, when we are applying a V over here, we assume that the gate is not having any signal. So, this is going to be AC ground, and then the other MOSFET provides only the small signal resistance RO4 and the NMOS RON. So, basically we are having the expression of our output because of a applied signal over here. Likewise, we can take the signal at the gate of this this PMOS and then find out the expression of the output voltage with respect to this signal. And while doing that, similarly, we will assume that the other signal over here is set to 0. So, in that case, I have V which is applied at the gate of this PMOS. We are going to get minus GM times the overall small signal resistance over here, and that is going to be equal to R parallel this 1 upon SCC. So, minus GM times R parallel 1 upon SCC, right, because if I am looking at this circuit as a common source amplifier where input is the M6, this PMOS device, at the load I have this overall small signal resistance RON parallel ROP, which is our R, and if this is set to AC ground, while analyzing the effect of this signal, this 1 upon SCC also appears in parallel with RON and ROP. Let me write it RON and ROP, and as a result I can write down the overall impedance minus GM times R parallel 1 upon SCC. Sorry. So, let me just complete this, R plus 1 upon SCC. So, this is the overall expression that you get because of the combination of these two signals at the MOSFET gate and at the input terminal of this capacitor. And then I can take out R upon R plus 1 upon SCC, and I have 1 minus GM times 1 upon SCC coming. So, from here we can see what is the value of the 0 that we were expecting. So, let me call this GM2, because ultimately this is the GM of the second stage. So, following our previous notations, I should write it GM2, and as a result I have the omega 0 given by GM2 upon CC, because at that frequency this term will be cancelling out and you will get an overall gain approaching 0. So, this is the 0 frequency that we are going to have. Now, in the overall response, if I look at the overall response, I have the first stage which is giving us an inverting gain. So, from there we have inverting gain coming into picture, and an overall 180 degree phase shift coming from there, and we have this second stage once again giving us a 0 term coming over here. So, if I incorporate the gain of the first stage, I already have a 180 degree phase shift because of the first stage, and then we have a second term over here. Let me simplify this a little bit further and arrive at relatively simplified expression. So, you have SCC minus GM2 upon SCC. So, this is an overall expression we are obtaining, and then I can take out CC from here. Now, if we look at frequencies which are much higher than omega, much higher than omega 0, at those frequencies we have the S term being dominant. So, this will lead to effectively increase in the magnitude of the gain. But if we look at the overall board plot, we of course have the other two poles, assuming that the two poles are coming at higher frequencies, at relatively lower frequencies as compared to this 0, we already have a gain decaying with minus 40 dB per decade slope. And just to justify that, yes, this is 0 which is a sufficiently higher frequency, we see that the overall impedance 1 upon GM coming at this node is sufficiently small. As a result, this 0 can be expected to lie at a relatively high frequency as compared to the pole P1 and P2 that we had in our original amplifier. So, in the compensated amplifier also, because the P1 and P2 are defined by the relatively high impedance nodes and the capacitance values which are sufficiently larger, we can assume that this particular 0 is at very high frequencies as compared to the dominant pole. And if we assume that it is also higher than the second pole, we are having 40 dB per decade slope before this 0 comes, because the earlier two poles are going to contribute overall 40 dB per decade decay in the gain before this 0 approaches. So, if I assume that that is true, so the overall board plot, you have the P1 and P2 suppose coming at relatively lower frequencies. So, after P1 you had minus 20 dB per decade slope, and then after P2 you have minus 40 dB per decade slope, and then you encounter this 0 in the numerator expression. And after this we can say that once you cross this 0, this omega term become dominant, you can ignore the second term. As a result, this is going to cancel out with the other two terms that you get till this point. So, till this point the expression of the overall gain was dependent upon omega square, but after the 0 you get another omega in the numerator, right, because of the two poles. Remember, you have 1 plus S upon P1, 1 plus S upon P2 in the numerator, and then now you are having S minus Z term coming over here. So, if the S is much larger than Z, and also the S is much larger than P1 P2, then the overall expression that you get is S upon P1 times S upon P2, because in the denominator you can ignore this ones, and in the numerator you can ignore this Z once your S is much greater than this 0 frequency. As a result, you get once again minus 20 dB per decade slope. The slope goes back to minus 20 dB. So, you started with minus 20 dB, after the second pole you got to minus 40 dB, and then after the 0 you are again back to minus 20 dB per decade. And likewise, if I look at the phase response, what is the effect of the 0 on the overall phase response? Now, we have an overall negative sign coming because of the previous stage also, and you are having an iota omega term coming at this stage. So, it is going to, if I incorporate the previous stage negative sign, once again you are having an additional phase shift of 90 degree coming because of this particular pole after you cross the Z, and as a result once again the phase becomes all the more negative, and the magnitude is going to increase. So, as a result we are having an overall phase which will basically approach 180 degree much faster because of the 0, because it is going to make it all the more negative. So, you are having further phase degradation, and it is also degrading the slope. So, the slope of the decay of the gain has been reduced and the phase is degrading further. As a result, the possibility of encountering instability can be enhanced, because the rate of decay of the gain has been reduced, at the same time the rate of decay of the phase is getting increased. As a result, this particular 0 can reduce the phase margin, and for that we need to address this issue, and we need to make certain modification in the circuit so that the 0 can be eliminated. So, let us get back to this point and look at the circuit solutions to eliminate this 0 in our amplifier through couple of circuit schemes.
So, in the expression that you have found out for the 0, there is one term of 1 plus R S C C in the denominator also.
Yes.
So, if you are saying S is that 0 is coming at a high frequency, so can't we assume that in the denominator that SRCC term is also going to come, that expression that you have written?
So, this R is much lower frequency. So, here if I look at the, so what do you mean by it is going to come means, can you elaborate?
The last expression that you have written S minus Z by 1 plus S by T1 into 1 plus S. Wouldn't there also be a term in the denominator SRCC?
In the denominator?
Yeah.
So, that is if I look at S upon P over here. So, that P is at a much lower frequency, because this R is going to be much smaller than this GM. So, you have the other poles, like if I look at the so you also have another expression. So, if I look at the R, and so if I assume that it comes at a frequency which is much lower than this GM, even then you get a overall reduction in slope. And if I compare what is the value of this. So, if you look at R and CC, R is the overall output impedance coming at this point, and CC is the equivalent the CC value that you have obtained. And if I look at the other expressions which are coming because of the poles at the two nodes over here and here. So, we have the pole because of the second node going to much higher frequency because of the reducing impedance of CC. So, that term has not been taken care over here. So, here we are ignoring the other circuit combinations, because you have a high impedance node coming over here, and we following our arguments in the earlier discussion, we analyze that this impedance is going to go lower. Here that assumption has not been taken. So, here just to show the effect of the 0, and without considering the degrading impedance over here and the drain and gate getting short circuited. So, those things have not been incorporated over here. So, this is just to using first order equations just to show that how the 0 is appearing, without considering the other effect where the CC connecting the drain and gate is effectively getting short circuited, and it is reducing the impedance, which is pushing that pole to high frequency. So, if you do exact expression, like if you write down the transfer function without considering any Miller effect and find out the exact expression for V out and V in, then you will get the expressions for the original poles and zeros at different nodes without having any approximation involved. And there again you can find out the x expression of 0 coming in the numerator along with the terms in the denominator, factor them out and get the expression for the exact poles, and there you can take approximation and arrive at more exact value of these poles. So, here while considering the effect of 0, just to show that the mechanism is what is the mechanism of originating of the zeros, we are using this model while ignoring its connection with the previous stage and the impedances is provided by the previous stage. So, this is once again just to do a hand calculation and show you a quick analysis. Exact analysis is a lot more tedious and it will lead to a second order or third order expression in the denominator if I find out the expression of V out versus V in using S domain analysis. So, that leads to exact expression for poles and zeros where you are not doing it in isolation. There is a second stage and then the first stage, that is more complete.
At a frequency very greater than that, the phase difference should become like it should be plus 90 degree now.
No, so here you have minus sign is also incorporated. So, if you look at the previous stage, you have a negative sign coming because of the previous stage and you are having the iota omega coming over here. So, if I look at the signal from here, you have overall negative sign coming from the previous stage, and multiplied by that it will give you an expression which is minus gm pi cc minus gm. So, that has already that is already giving you a negative sign. So, this will basically gm upon cc minus s. So, it will get inverted. So, once again this is an approximate analysis where we have not considered the interaction of the previous stage with this stage. We are just assuming that you have a signal applied over here from an ideal source, and we are considering only the 0 coming at this point through this path and not considering the effect of the impedances provided at the previous stage. So, that is an approximation involved here just to isolate this analysis and show you the origin of 0. Okay. So, resume our discussion on this 0 and look at the circuit techniques which can be applied to remove this 0 or cancel it with some other terms in the denominator.